Welcome to AP Podcast 11.2. This is going to be on the energy of making solutions. And we're also going to be talking a little bit about the solubility effects of, or at least the factors that affect the solubility. So we've just got done talking about solutions in 11.1, and we're looking at another energy term here. Notice we're talking about the heat of solution. Right? Now, you guys seen enough of these delta H's to last a lifetime, right? But there's a heat of solution. So we're talking about the energy involved in making the solution. And the easiest way to think about this is kind of think of it as 3 steps. If you do that, some of this will make a little more sense. So let's just talk about what happens if, let's say I'm going to make up something like a saltwater solution. Well, step 1, the solute has to break up. All right. So if you can imagine it being something like a salt crystal, it would take a little bit of energy to get that to happen because you've got to overcome all those ionic charges. So that's going to happen. So that's going to take some energy, right? And then if you want to expand the solvent, and for our examples, most of the time we're dealing with water, right? So if I want to expand the solvent, what I've got to do is overcome those hydrogen bonds, right? If I have a water molecule, and we've got that attraction to another water molecule, in order to allow this mixing, we've got to break those bonds. So there's 2 steps that require a little bit of energy. Now the third step is where we're mixing them. And this is often going to be exothermic. At least if it's exothermic, the solution is being favored. So just kind of now looking a little closer at step 3, because that's kind of the critical step. That's the step where we're going to mix the 2 things together. We're mixing the solvent and the solute. Now this really depends upon what kind of things you're mixing. For example, if you recall that oil is nonpolar, right? And of course water is polar. We know those things do not mix. They do not mix. Well, that's part of the problem that we're looking with if we're thinking about what kind of value it have for H3. If they are attracted to each other, like, for example, if I have ions, right? If I have ions that have charges and water molecules that are polar, those things are going to attract each other, and this H3 is a large value, which is good, and it's also negative, which is good. But if we have molecules that can't attract, like oil and water, this H3 value is really small, and it's still going to be negative. It's still going to give off a little energy, but it really can't overcome the forces of H1 and H2 in order to get H solution to be a negative thing. So H solution in that case becomes positive. And since it's positive, it's not really a favorable thing, and therefore we don't see oil and water mixing hardly at all. I mean, there is some mixing on a microscopic level, but for our purposes, there's not really any mixing. So that's kind of where we get this whole like dissolves like. So polar things will dissolve in polar things. And the same with nonpolar and nonpolar. However, these 2 will not dissolve in each other. And it really has to do with the energy involved in those 3 steps. So things that favor the solution, a solution being made, are negative values for the heat of solution. If we get an increase in entropy, right? That means S would be positive. And it turns out that if the heat of solution is small and positive, which is not favorable, you could still get it to form because of this factor right here. Okay? You can imagine that a solution is going to have a lot more disorder than the 2 things separated. There's a lot more spaces for those molecules to be when it's all mixed into a solution, rather than them staying separate. So that's kind of the driving force of making solutions. Now let's look at the structure, because there's some structure issues involved in solubility. When we talk about what I just talked about with the oil and the water, the reason they're mixing is because of these polar bonds. All right, if you got like dissolving like and so on, and so this is right from. So when we look at something like this, we've got two molecules, and this is right out of your textbook. And look at all the OH bonds here. This thing is polar right here. Okay, and that's vitamin C. Now, vitamin C is known as a water-soluble vitamin. You can take as much as you want, and anything that's excess we just get rid of in our urine. However, something like vitamin A and all this whole chain is, this molecule is essentially nonpolar. I know there's a little OH out there, but this whole molecule is essentially nonpolar, and so this is a nonpolar thing, and this is fat soluble, and so vitamin A is stored in our fat, which happens to be also nonpolar. So we're back to that like dissolves like thing. All right. Now another thing that affects solubility with solutions is there is a pressure situation. Now if you think about a pressure of a solid liquid, if you change that pressure, it's not going to affect how much it's going to dissolve, because you can't compress them. However, you can definitely compress gases, as we well know. And so when you dissolve gas, it turns out that by causing a pressure above the liquid, you can get more of the material to dissolve into the liquid. So if we think about our equilibrium situation, we kind of talked about this in chapter 10, we've got that situation. And then if I go ahead and increase the pressure up here, that pressure is going to cause these molecules above the liquid to be forced into the solution. It's going to change the equilibrium a little bit. And so if you want to calculate this out, and I got to tell you, in AP, this is not something we ever calculate out. I mean, it's just something that you need to understand, that gases will dissolve more if the pressure is greater. But if we were to calculate it out, we'd use Henry's law, which just basically relates the pressure to the concentration of dissolved gases by some sort of constant. So anyways, that's a very important concept, though. This pressure above here is going to definitely affect how much dissolves. And you can think about any kind of carbonated beverage, right? Pop? I mean, think about that. You shake a bottle up, you open it up, stuff goes spewing everywhere, right? And that's because there's such a great pressure in that bottle that the gas is dissolved into the liquid. But that's a real touchy, sensitive liquid right now because it's got a lot of gas. It's got more gas than it can hold at normal pressure. So as soon as you release that pressure, that gas wants to come out. And you couldn't do that unless you had a pressure situation. Now the other way we could affect solutions are with the temperature. And if you increase the temperature, you can, for the most part, dissolve more stuff in a liquid. Now you don't know it for sure, but most of the time it does. And in order to see for sure if that happens, you really just got to look at a data table or a graph. But if you've ever tried dissolving something like, well, let's show you the graph. Here's a graph right here. This shows you all the different things. And look at something like this. Look at sugar. If you've ever had the joy of making rock candy, you can see the graph going up and up and up. And temperature, this is temp down here. So as the temperature is increasing, more and more, these are let's just say these are grams, more and more of the sugar can dissolve in the water. All right, and it's that way for many things. Now for sodium bromide, no, and for cesium sulfate, no, but for most things, the temperature is going to cause an increase in the dissolving rate. And then last but not least, pardon me. When we have gases are very predictable. As the temperature increases, the solubility decreases. Take a can of soda, stick it on a countertop, come back later after it's gotten out of the fridge and been at room temperature, and the molecules in the liquid are now escaped. And if you think about it, if I heat up a solution, the kinetic energy of that solution is increased, the molecules are moving faster, and the gases trapped inside that liquid will be escaping. And so that definitely affects the solubility of things. All right? So let's just look at one simple problem that we would be asked to do. And if we remember the like dissolves like and how temperature and pressure affects, these problems are pretty straightforward. So look at question 38. Which solvent, water or hexane, would you choose to dissolve each of the following? Well, in this case, we're talking about water, right, being polar, and hexane, look at that, that's nonpolar. So if I'm going to dissolve something in either one of those, I want to make sure that it's like. Like dissolves like. So what is this? Ionic compound, going to dissolve it in water. HF, right? There's the most electronegative element right there. There's another very polar thing, dissolving that. Octane. There's another nonpolar thing. I'll dissolve it in that. And here's another ionic compound. And so we'll dissolve that one in water. So there you have it, a little bit of solubility stuff. We'll practice a few of these problems in class, and we'll see you next time.